So now let's talk about vapor pressure lowering. When you add a non-volatile solute, the vapor pressure above your solution is going to drop. In other words, okay, so here's my uh, liquid in equilibrium with the gas, okay? If I were to contaminate my liquid, I'm going to put some solutes in there that are not volatile. What happens is there's going to be, okay, at the instant I do that, there's going to be a momentary increase in the rate in the net transfer of gas molecules back to the liquid. So the vapor pressure of your gas is going to be lowered. Okay, why would that happen? Well, think of it this way. Right. At equilibrium, let's imagine a surface here where you have, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just, to make things simple, let's just imagine you have 10, consider 10 molecules of water there at the surface, okay? And you've got water molecules up here also, right? So at equilibrium, the rate at which the water leaves the water molecules leave the liquid would be equal to the rate at which the water molecules go back to the liquid from the gas. What happens if you contaminate your liquid with a non-volatile solute? So what happens is, let's say 2 out of these 10 molecules is not water anymore because you've contaminated it. Okay, remember, in a solution, your solid is going to be spread out all over, right? So now 20% of your takeoff sites have been blocked. But the number of landing sites for molecules from the gas phase, okay, so if your molecules from the gas phase, the number of landing spots for them is the same, right? They can still land wherever they want, but the takeoff sites for the water molecules to go from liquid to gas have been blocked. Only 80% of the takeoff sites remain. So what do you expect? Then you say the tendency for the liquid to go to the gas phase has been lowered. And so what the net result is, when equilibrium is reestablished, the vapor pressure of your water is going to drop. The vapor pressure of your liquid is going to drop. Okay? So in fact, what's going to be the vapor pressure? If P star is the vapor pressure before you contaminated it, so P star is the vapor pressure of the pure case, okay, in the pure case. Then, all right, so now how much of it is blocked in this particular example? 20% is blocked, 2 out of 10. So you only now have 80% of the takeoff sites available for takeoff. So multiply this by the mole fraction of the water, okay, which is in this particular example that I gave you is only 80% now, right? That would be the new vapor pressure of the water. Okay, so going back up here, okay, so Raoult's law, okay, this observation is called Raoult's law, says that the partial pressure or the vapor pressure of a volatile component of your mixture, so if we say A is a volatile component of your mixture, once it's contaminated, okay, its vapor pressure is going to be lowered. Okay, so it's now going to be whatever the original vapor pressure is. So P star A, that's the vapor pressure if it was pure, multiplied by its mole fraction. Okay, so if we call A is A our solvent in this case. So A would be water if your solvent is water. So what happens then? Well, by how much is the pressure lowered? Well, we take the original vapor pressure, that's the vapor pressure that would be in equilibrium with the pure liquid, minus the vapor pressure that's in equilibrium with the solution. Okay? So P star A minus P sub A, that's your vapor pressure lowering. Okay? That's your vapor pressure lowering. So it's going to be equal to P star A minus the new pressure, which is P star A times XA. So what can I do with that? If I have P star A minus P star A times mole fraction of A, I can factor out P star A, right? So I factor out P star A. What's left inside? It's going to be 1 minus x of A. Okay? Distributive property, see? P star A times 1 is P star A. P star A times XA is P star A times XA. There. But what is 1 minus mole fraction of A? If you subtract the mole fraction of the solvent from 1, what does that give you? That's the mole fraction of everything else. So we call that XB, mole fraction of your solutes. So in this case, we say X of B is the mole fraction of your solute. Of your solute particles. Okay? So your vapor pressure lowering, then we can say, is equal to P star A times the mole fraction. So delta P, which is P star A minus PA, is equal to the original vapor pressure of the solvent when it's pure times the mole fraction of the solutes. Okay? What's a non-volatile solute? These are solutes that are ordinarily solids when they are in pure form. Okay, so they have a very low tendency to turn into a gas. So, clicker question right here. The vapor pressure of salt water at 100 degrees Celsius is A, less than 1 atmosphere, B, equal to 1 atmosphere, or C, higher than 1 atmosphere. Okay. So what's the answer? See how we did? That's very good. Vapor pressure lowering. Okay. At 100 degrees, if it was pure, the vapor pressure would be 1 atmosphere. So if it's contaminated, it's not pure water anymore, the vapor pressure will be lower. Okay, here's another clicker question. Which of the following has a higher vapor pressure of water at the same temperature? A mixture of 0.1 moles sodium chloride and 99.8 moles of water, or a mixture of 0.1 mole glucose plus 99.9 moles of water. Ready? Let's see how it did. Oh, 50-50. Alright, so I guess you need your phone a friend lifeline. 50-50 didn't work? Okay, so vapor pressure of water, let's call water A, is equal to P star A times mole fraction of water, right? Now, P star A is the same, right? In both cases, we're dealing with water. We're comparing water. So we just need to compare mole fraction of water. So what's the mole fraction of water? X of A in this case is moles of A. So for choice A, what's the mole fraction of water? Moles of water over moles total, right? How many moles of water are in choice A? 99.8 moles. What's the total moles in choice A? 99.8 for water. But how many moles of solute particles do you have? Is it 0.1? 0.1 times 2. Why do you multiply this 0.1 by 2? What do you know about sodium chloride in water? What does it do in water? It ionizes. It actually gives you 2 particles. Okay? So that's the idea behind colligative properties. You have to be looking at the total solute concentration of solute particles. So what's the mole fraction of water in this case? So 99.8 divided by, what's my denominator? What's 99.8 plus 0.2? 100. So my mole fraction of water here is 0.998. What about in the second case, in glucose? Mole fraction of water in choice B. Okay, mole fraction of water is 99.9. Okay, over the total. What's the total in this case? 99.9 plus, how many moles of glucose do we have? 0.1. What's the Van Hoff factor for glucose? Do you multiply that by anything? Multiply by 1, right? It doesn't dissociate in water, so you just add 0.1. 0.1 times 1. So that's going to be 99.9 over 100, which is 0.999. So in which case do you have a higher vapor pressure of water? Is it A or B? It's B. Okay. Higher mole fraction of water, higher vapor pressure of water. Which one will you get a larger vapor? In which case will you get a larger vapor pressure lowering? Then it will be the opposite. Okay. So here's a straightforward question that just applies the formula. What is the vapor pressure of water in a solution at 85 degrees? Okay, containing 18 grams of glucose, 5.844 grams of sodium chloride dissolved in 500 grams of water. The vapor pressure of water is 433.6 millimeters of mercury. You might be wondering, where did this come from? This is something you're going to have to look up. Okay, so in cases like exams where you don't have access to that kind of information, that would be given to you. So partial pressure of water, I call that PW, would be PW star, okay, times mole fraction of water. How do I get mole fraction of water here? Mole fraction of water is equal to moles of water over moles total. How many moles of water do I have? I have 500 grams of water. How do I change that to moles? 500 grams over 18.02 grams per mole. Okay, that cancels grams. Okay, how do I get total moles? Well, part of that total would be the water, right? So 500.0 grams over 18.02 grams per mole plus, so grams cancel out there. What else do I have in my mixture? Glucose. I have 18 grams of glucose, C6H12O6, non-volatile solid. So I have 18 grams. What's the molar mass of glucose? We've done this before. C6H12O6, 180.2 grams per mole. Okay. Grams cancel out. Plus, how many moles of sodium chloride? How do you calculate mole sodium chloride? Grams divided by molar mass. So 5.844 grams of sodium chloride divided by how many? What's the molar mass of sodium chloride? 58.44 grams per mole. Am I done? Other than punching this into a calculator? Not quite. Why? What do we know about sodium chloride? It gives you twice as many particles in solution, so I have to multiply this by 2. Okay? So that's your mole fraction of water. So all you have to do now is take all of these numbers, plug that into mole fraction of water, and what goes into here? That would be the partial pressure of pure water. Okay? I guess you can do that on your own. Huh?